What happens when you take the exact same data pipeline and run it two different ways? On one side, traditional ETL, extract the data, transform it, load it into the target system. On the other side, LTAP, a more modern approach designed around faster data movement and processing. But here's the question, which one actually wins? And more importantly, where does the performance difference come from? Today, we're going to build both pipelines, run the same workload for each one, measure the execution time, CPU memory, and data throughput, and reveal the winner. Before we start benchmarking, let's define exactly what we're comparing. Traditional ETL follows a familiar pattern: extract data from the source, transform it in a processing layer, and finally load the transformed data into the destination. This architecture has been incredibly successful. It's predictable, it's mature, and practically every data engineering team understands it. But there's a problem. Every additional stage can introduce latency. Data may be copied multiple times. Intermediate files may be generated. Transformations may require additional compute. And large batch-oriented workflows can create a significant delay between the moment data appears and the moment it's actually available downstream. LTAP takes a different approach. Instead of treating data movement as a sequence of isolated batch stages, the goal is to make the movement and processing path more direct and efficient. And that's exactly what we're going to test. For this benchmark, we're going to keep the comparison as fair as possible. Same source, same dataset, same transformation logic, same destination, and ideally, the same underlying hardware. Our test dataset contains 100 million rows, 25 columns, around 100 gigabytes of data. The workload isn't just a simple copy. We're going to perform realistic operations: filtering, joining, aggregating, and finally writing the results to our target. We're also going to measure 4 things: total execution time, throughput, CPU utilization, and memory utilization. And there's one more metric I care about: time to usable data. Because processing 100 gigabytes in 5 minutes doesn't help much if downstream users still have to wait another 10 minutes before the data is actually available. Let's start with the architecture most data engineers already know: traditional ETL. The first stage is extraction. We pull data from our source system. That might be a relational database, an API, CSV files, application logs, or another data warehouse. The extracted data usually lands in some intermediate location. Then the transformation stage begins. This is where we perform operations such as filtering, cleaning, type conversions, joins, aggregations, deduplication, and business rules. Finally, the transformed data is loaded into our destination. Simple enough, but notice something: we're potentially moving the same data multiple times, and every movement costs something. I/O, network bandwidth, serialization, deserialization, storage operations, and compute. The more data we process, the more those costs matter. Let's build our baseline. The exact implementation can vary depending on your stack, but conceptually, our pipeline looks like this: extract, transform, load. The important thing isn't the programming language. The important thing is the architecture. Extract, transform, load. Now let's run it. And there we go. The first benchmark is complete. Let's record the result. Don't worry about the exact numbers yet. The point of this first run is establishing our baseline, because if we don't have a baseline, we can't claim that LTAP is actually faster. Now comes the interesting part. So, where does the time actually go? Let's break it down. First, extraction. We have to read the source. Then, transfer. The data has to move. Then, transformation. Our compute layer processes the dataset. Then, serialization. Processed results may need to be encoded. Then, loading. The target system receives and stores the data. And depending on the architecture, we may also have intermediate storage. Each individual step may look inexpensive, but at 100 gigabytes, or 1 terabyte, or 10 terabytes, small inefficiencies become very expensive. This is where modern data movement architectures become interesting. Now let's switch to LTAP. The key idea is simple: reduce unnecessary movement and processing overhead. Instead of thinking about the pipeline as 3 disconnected batch stages, we want a more optimized path between the source, processing layer, and destination. The exact architecture depends on the LTAP implementation we're using, but conceptually, we're trying to reduce redundant copies, unnecessary serialization, unnecessary storage operations, batch waiting time, and repeated data movement. And that's where our benchmark gets interesting. Let's rebuild the exact same workload. Remember, same source, same data, same transformations, same target. The only thing we're changing is the pipeline architecture. Again, the exact API will depend on your LTAP implementation. The important part is that we are avoiding unnecessary intermediate movement wherever the architecture allows it. Now, let's run the benchmark. The pipeline is running, data is moving, transformations are executing at a time. Now let's put the numbers side by side, and there it is. LTAP completed the workload significantly faster in this test. But here's the part that matters. The speed improvement isn't magic, it's architectural. First, data movement. If you eliminate unnecessary copies, you're immediately reducing I/O and network overhead. Second, serialization. Moving data between systems often means converting it into an intermediate representation. That conversion costs CPU. Avoiding unnecessary conversions can reduce processing overhead. Third, intermediate storage. Traditional pipelines frequently rely on staging layers. Those layers are useful, but they can also add latency. And finally, batch waiting. Traditional ETL often works in discrete stages. Stage 1 finishes, then Stage 2 starts, then Stage 3. A more optimized architecture can reduce some of that waiting. Now here's where we need to be careful. A benchmark doesn't mean LTAP is automatically better for every workload. It isn't. If your dataset is tiny, the overhead difference may barely matter. If your transformations are extremely complex, the transformation itself may dominate the runtime. And if your pipeline depends heavily on external systems, your bottleneck may be somewhere completely different. If the source only delivers data slowly, making the processing layer faster will magically fix the source. That's a critical lesson in performance engineering. Optimize the bottleneck, not the technology that happens to be most exciting. Now let's make the benchmark more interesting. Instead of running one dataset size, let's scale the workload. We'll test 10 gigabytes, 100 gigabytes, 1 terabyte, and if the infrastructure allows it, 10 terabytes. Because a system that looks similar at 10 gigabytes can behave completely differently at 10 terabytes. And this is where architecture really matters. As the dataset grows, fixed overhead becomes less important, while data movement, I/O, compute, and network efficiency become increasingly important. There's another metric we haven't talked about yet, cost. Imagine traditional ETL takes 30 minutes, while LTAP takes 15. If both use exactly the same infrastructure continuously, the faster pipeline may also consume fewer compute resources over the same workload. But don't automatically assume faster equals cheaper. You need to measure compute time, storage, network transfer, memory, infrastructure utilization, and operational complexity. So when does traditional ETL still make sense? A lot of the time. If your organization already has a mature ETL platform, if your pipelines are stable, if your datasets aren't enormous, and if reliability and simplicity matter more than shaving minutes off execution time, traditional ETL can be the right choice. There's a huge advantage to mature technology. It works. Your team knows how to operate it. Monitoring is already in place. Failure recovery is understood. And the organization may already have years of tooling around it. LTAP becomes more interesting when data volume increases, latency requirements become tighter, and unnecessary data movement becomes one of your biggest bottlenecks. Think real-time analytics, large-scale lakehouse workloads, AI data pipelines, high-frequency ingestion, massive datasets. This is especially important for AI workloads, because modern AI systems aren't just processing models, they're processing enormous amounts of data, training data, feature data, embeddings, retrieval datasets, logs, evaluation data, and telemetry. When those pipelines become large enough, data movement itself becomes a performance problem. So let's summarize. Traditional ETL is mature, predictable, well understood, and still extremely useful. But its staged architecture can introduce additional data movement, storage, serialization, and latency. LTAP takes a more optimized approach to moving and processing data. And in workloads where data movement is the bottleneck, that can translate into significant performance gains. But the real winner isn't the technology with the coolest acronym. It's the architecture that removes your actual bottleneck. So, LTAP versus traditional ETL. Is LTAP faster? Potentially. And in the right workload, dramatically faster. But don't take a benchmark from one environment and assume it applies everywhere. Run your own workload. Use your own data. Measure your own infrastructure. And most importantly, measure the entire pipeline, not just the transformation step. Because sometimes the slowest part of your data pipeline isn't the processing. It's everything happening around the processing. If you found this benchmark useful, subscribe to AI Learning Hub, Byte-Size AI Learn, for more practical AI, data engineering, and modern infrastructure tutorials. And if you want, I can do a follow-up benchmark where we take this even further. LTAP versus ETL versus ELT versus streaming pipelines, with the same dataset and the same workload. That comparison gets really interesting. I'll see you in the next one.